So, welcome to the second lecture of this week. So, we had started for our dependency parsing formulation, and we defined what is the problem and what are the very formal conditions on a dependency graph in the last lecture. So, we are given an input sentence, I want to obtain a dependency graph for that sentence, and for that we discussed that there are certain ways we can handle this problem, and in this course we will mainly focus on the approaches that use some sort of label data for this task. So, it will be some sort of machine learning task for finding out the dependency parse for a new sentence. So, now, in the next 4 lectures in this week, I will cover 2 different methods for the same problem, but before discussing the methods in detail, let me try to give you a basic intuition on what we are trying to achieve. And this will also help you to understand that if you are given a new problem and you want to take it in a machine, you want to solve it in a machine learning based method, then how you should go about it. Okay. So, let me take this case. So, I have a sentence that contains some words. Okay. This is some arbitrary sentence, this is a new sentence, I might not have seen it before, and my goal is to come up with a dependency graph, okay, where nodes are different words and there are certain relations R1, R2, etc. are certain relations. Okay. This is my dependency graph. So, I want to go from the sentence to my dependency graph. Now, suppose I want to do it in some sort of systematic manner by using some sort of data. So, what I will do? I will try to convert that to some sort of configuration format, okay, some initial configuration. So, that means there will be a function that will take any sentence as input and convert that to an initial configuration. Now, I will define some operations that I can make on this initial configuration, okay, and that will take me to some intermediate configuration. And I should be able to keep on doing these operations until at some point of time I arrive at a terminal configuration. And terminal configuration should be something that resembles a dependency graph. Okay. So, my whole task is now starting from the input sentence, convert that to an initial configuration, apply some well defined operations and go to intermediate configuration until you finally reach a terminal configuration. That may be deterministic, may not be deterministic. So, now, this is my whole thing. This is my sentence and this is my dependency graph, and operations are something I do not know, but I need to define. I need to find out for a particular configuration what are the operations that I should take. Now, where does machine learning comes in here? So, this looks like very deterministic. What is the problem? The problem is there may not be a single operation. So, I should have a way to find out for a given configuration what is the operation that I should take, and that I am trying to learn from the data that I have. So, that is where the machine learning comes in. So, we have data where we have a set of sentences and their corresponding dependency graphs. Okay. So, there I can find out for what configuration what was the operation that I had taken, and I will use that to learn for a new sentence or a new configuration what operation I should be taking, so that given any new sentence I can actually find out its dependency graph. And this is just a generic idea. We will see specifically how it will be used in the 2 different methods that we will cover in this course. So, now the first method that we are going to cover is a transition based parsing method. Okay. So, we will see its formulation. So, what is the basic idea? So, it is similar to the intuition that I had provided earlier, that is I have to derive a single syntactic representation, it is called the dependency graph, via a deterministic sequence of elementary parsing of actions, and this is what we were saying as operations. I start with a sentence, I keep on having certain operations over that until I arrive at some dependency graph. So, now in this particular case of transition based parsing, what do I mean by a configuration? What will my configuration look like? So, by configuration I will mean a triple, that is a stack, buffer and a set of arcs. So, that is at any point I can define a configuration. In the configuration I will have a stack where there will be some set of words that have been partially processed. Then the buffer, it will contain words that are remaining, and whatever arcs I have already obtained via my operations, this will be in the set of arcs. So, at the bottom of this slide you are seeing one example of a configuration. So, this is for the sentence, he sent her a letter. So, this is an intermediate configuration where you have the words sent her a in the stack. So, you are partially processed at this point. The word letter and punctuation are in the buffer, they are remaining, and there is already an arc between the words he and sent, and he is the subject of the word sent, the verb sent. So, this is an intermediate configuration. Now, how do I formally define my whole transition system? So, formally, so it will be very analogous to what I started discussing. Okay. So, I need to define what are my possible configurations, how do I go from a sentence to an initial configuration, and which configuration will I call as a final configuration, and what are the operations I should make so that I can transit from one configuration to another configuration, and that is where the name of transition systems also comes in. So, then formally we will define dependency parsing transition system as a quadruple that has CT, CS and CT. And what are these? Capital C is a set of configurations, all the configurations that are possible. Now, capital T denotes a set of transitions, and each transition takes me from one configuration to another configuration, from C to C, one configuration in the set C to another configuration in the set C. Now, CS will be an initialization function that you will give a sentence as input, and you will find the initial configuration as output, and then you will have a set of terminal configurations. So, that means whenever you reach a terminal configuration via your operations, you will stop and you will call it as your dependency graph. Now, whenever you are given a sentence X, what is my transition sequence? So its sequence will be a set of configurations starting from C0 to Cm, and what are the conditions on those? C0 is something that you can derive from the sentence. Okay. So, suppose X is the sentence that you are giving as input, and you want to find out its dependency graph. So, now what is the idea? You have a function, initialization function, you apply this function over X and you get a transition, you get a configuration C0. Now, you keep on applying various operations and get C1, C2 up to Cm, and Cm is in the set of terminal configurations. Okay, this is my initialization function, set of terminal configurations, and C0 to Cm all are in the set of configurations. And what is the relation between any two conjugative Ci and Ci plus 1? Relation would be I can obtain Ci plus 1 by making a transition over Ci. Okay. For some transition I have defined in my set capital T. So, this is my process. Start with a sentence, apply the initialization function, get the initial configuration, keep on applying various transitions until you obtain a terminal configuration. Okay. Now, as per the transition system that we have defined, what will be the initialization? Initial will be simple. So, I have to define what is my stack, what is my buffer, and what are my arcs, because when I am starting with a sentence W1 to Wn. Okay. Initially, my stack should contain the set of partially processed words. So, there is nothing that is processed right now. So, my stack will be empty. My buffer should contain the set of remaining input words. So, remaining words are all the words W1 to Wn, and my arc should contain whatever dependency relations I have already found. So, it will be empty. This will be empty set. This is my initialization. Now, what will be the terminal configuration? At termination, so the idea is I should not have any words remaining in the buffer. So, my buffer should be empty. So, terminal condition I can define as stack would have some it may or may not have some words, buffer should be empty, and I will have obtained a set of args. So, this is important, my buffer should be empty. Stack may or may not contain some words, and args will have some dependency relations already. So, now once you know what is my initial configuration, what is my termination condition, now what is remaining in this whole thing? We know all the possible set of configurations. What is remaining is what are all the possible transitions that I can take for going from one configuration to another configuration. How do I move from an initial configuration by a sequence of operations so that I arrive at a terminal configuration. Okay. So, now in this system there are 4 transitions that have been defined. Okay. So, that means for any configuration you can take one of these 4 transitions. So, in this slide I am showing you the 4 different transitions that you can take. So, how you should read it? So, in the left the names of the transitions, left arc, right arc for a dependency D, reduce and shift, these are the 4 transitions possible. Now, for each transition like left arc, you will have what is the configuration that is the input to that or with which you are starting on top, and what is the configuration that you will end up with starting from this configuration. If you apply left arc, what configuration you will arrive at. And finally, in the right, if there is something that is a condition, what is the condition under which you can apply this transition. This is just a necessary condition. You need to have the condition satisfied to be able to apply this transition. So, for example, if I see the left arc transition, what does it say? It says that I can apply it when the stack contains some words, and I have been shown here the last word in the stack. I can also call it the top of a stack, the word is SI. Buffer contains some words, WJ is starting from WJ, top of buffer is WJ, and I have some set of arcs A. Now, what do I mean by left arc? Left arc means I am making a transition from WJ to WI. Yes, this is the left arc, because the words are occurring in the same order that they occur in the sentence. So, there is a arc from WJ to WI. So, what is the head here? WI is the head and dependent is WJ is the head and WI is the dependent. Okay. So, now there is also a condition here. WI should not already have a head, and let us try to understand this condition. So, what am I saying? My stack contains some words and top is WI, buffer contains some words starting from WJ, and I am making a left arc. So, left arc, as the name says, will be from buffer to stack, and we are always operating on the top words in buffer and stack. So, I am making an arc from the top word in buffer to the top word in stack. This is a left arc. Now, what is the condition? Condition is WI should not already have an head. Now, why is this condition? You see, here if I am making this transition, we are saying that WJ is the head of WI. Now, if WI already has a head, I cannot apply this. Why? Can you see what particular condition in dependency parse does it violate? So, dependency parse has a single head constraint. Okay. So, this is a single head constraint. So, that says each word can have at most one head. So, if WI already has a head, then I cannot apply this particular transition. Okay. So, that is left arc can be applied only if Wi does not already have a head. Now, suppose I apply left arc. Now, I start with a configuration like that. What is my resulting configuration? So, resulting configuration would be, I will remove Wi from the stack. Okay, it will contain all the words except Wi. Buffer will remain as it is, and my arcs will be, I have got a new arc. What is that? Wj dependent is Wi. This is my new arc. Okay. So, I have removed Wi from my stack. Now, you might have this question, why am I removing Wi from the stack? If a word is removed, I cannot put it back. So, I can remove a word from the stack only if I am sure that all its relations have already been captured. Now, so the question here is, can this word Wi have any more relations with any words? So, if Wi has any relation with the words that occur before Wi, it would already have been captured at this point, because these are already partially processed words. So, the only relation Wi might have is with any words after Wj. Now, let us take a scenario. Take a word here Wk. Okay. Now, what kind of relation Wi might have with Wk? It can be either an incoming arc, or it can be an outgoing arc. Okay. Now, can it have an incoming arc from Wk? It cannot. Yes, because it can have only one head. So, this is not possible. Now, what is the other condition? That can it have a outgoing arc to some word Wk? Now, what do you think about it? Is that possible? Now, if you think again about the formal condition that we have defined, what condition is it violating? Remember the condition on projectivity. If there is a relation from j to I, then from I the next dependent can be only on this side of j, it cannot be on that side of j. Okay. So, this has to be either in between, that is not possible, or here. Okay. So, this is also not a possibility. So, that means Wi cannot have any further relations. So, that is why we can remove Wi from the stack, and this is my stack that contains everything other than Wi, buffer remains the same. Now, let us look at the second transition, right arc. So, now right arc is, you are making a relation from Wi to Wj. Wi is the head and Wj is the dependent. There is no condition that you have to see here, and when you apply this particular transition, what do you obtain? Wj goes to the stack. So, I do not remove Wi, and Wj goes to the stack, and I get a new arc. Okay. So, now again you can try to think here, why we did not remove Wi from the stack, or why we did not remove Wj from the buffer and remove it altogether, why we are not doing it, and try to think in terms of the constraints that we have put over our dependency parse. Okay, and you will come up with some nice intuitions that why we are defining the transitions in this particular manner. So, we have seen the justification for the previous case. Now, try to give justification yourself for this case. But here the difference is that now the transition is from Wi to Wj, and accordingly I am getting a new arc. Then we have two more transitions, reduce and shift. What is reduce? In reduce, I remove the top word from the stack, and the condition is Wi already has a head. If Wi already has a head, I can remove that. And finally, the fourth transition is shift. What is that? I take the top word on the buffer and shift it to the top of stack. and these are the 4 transitions. Now, the main thing here is when you are at a particular configuration, you might be able to take more than one of these operations or transitions, and your task would be to find out what is the transition that I should take in a particular scenario. So, I hope the 4 transitions are clear. Let us see a particular example and how do we apply these transitions. So, we will take a very simple example. So, what we will have? We will have a sentence, he sent her a letter, and we also know the dependency parse of the sentence. Now, once you are given the sentence and its actual dependency parse that you want to obtain, you have to find out what are the transitions that you should be taking at each intermediate or initial configuration, so that you can end up with the dependency graph. So, let us do this exercise. So, here this is my sentence, he sent her a letter, and there is also a punctuation mark. How do we start? Find out what is the initial configuration. Now, how do you convert this sentence to the initial configuration? Stack would be empty, buffer would contain all the words, and args would be empty, and that is your initial configuration. Stack is empty, buffer contains all the words, and args is empty. Now, your task starts. This is the initial configuration. Now, what is the transition that you must be taking here? So this one is relatively easy. I cannot do left arc. Left arc means a arc from he to a word in stack. There is no word in stack, so there cannot be any dependency relation. Similarly, right arc is not possible because there is no word on the top of stack. I cannot do reduce because again there is no word on the top of a stack. So, the only transition possible is shift. I can take the top word in the buffer and move that to the stack, and this is what I will do. I will take the transition as shift. So, if I do that, how do I modify my configuration? So, if I do a shift, he will go from buffer to the stack, and that is what I will obtain. Now this is my intermediate configuration. Now, again you have to find out what is the transition that you must be taking at this point, and that is where you will look at the dependency graph that you want to obtain, and you will see, is there a relation you want to establish between the top of stack and top of buffer. So, in the past you are seeing he is a subject for sent. That means, you can establish a relation between sent and he, and what will be that? It should be from sent to he, so it should be a left arc relation. So, that means I can take a left arc transition at this point, and if I take a left arc, what will be the output configuration? I will remove he from the stack, buffer will remain as it is, and arcs I will get one more arc, and that is what is my next configuration. Stack is empty, buffer contains the remaining words, and I have one arc obtained. Now, you are at this configuration. Now, what is the transition you should take? Again, whenever stack is empty, the only transition possible is shift. So, I will do a shift. Okay. Now, I have one word in the stack sent, and there are some words in the buffer her, a, and letter. Now, what is the transition you can take at this point? Again, you will try to have a look at the dependency parse. You will see if there is a relation between sent and her. Yes, her is a dependent and sent is a modifier. So, sent is the head. So, what is this transition? From sent to her, it will be a right arc. So, I will take a right arc transition, and what will be the output of right arc? The word her should go to the stack, and I will get a new relation in my arcs. So, this will be my configuration at this point. I have the words sent and her in the stack, a and letter in buffer, and I got the arcs. Now, I am at a point where I have some words in the stack, I have some words in the buffer, and now I have to see what is the transition I should be taking here. So, let us have a look. Can I take a left arc or right arc? You see, her and a are not related in my dependency parse. So, I cannot take a left arc or right arc. Now, what are the possibilities? The possibilities are, I can either take a reduce or shift. Yes, both are possible. Now, how do I choose between reduce and shift? And there is a rule of thumb for choosing between shift and reduce. And the idea is, if you find that there is a word in the stack not on the top, just a word before the top, any words before the top of the stack that connects to the word on the top of the buffer, you do reduce, otherwise shift. Of course, you can do reduce only if you have already found the head for the word. So, in this case, should I take reduce or shift? Let us take this rule of thumb. Is there a word in the stack below her that connects to the top of buffer? There is not. So, I cannot take reduce, I should take shift. So, if I do shift, that is what I get. I take a shift, I now have sent her a letter. Now, once I am at this configuration, what is the next transition I will take? This time it is easy. There is a relation between letter and a, this should be left arc. Left arc means I will remove a. Okay. So, now again I am here, there is no relation between her and letter. So, now, so that means you can choose between reduce and shift. So, use the rule of thumb again. Is there a word below the top in the stack that connects to the top of buffer? And you will see yes, the word sent in the stack connects to the word letter in the buffer. So, here you can do reduce, and you do reduce, and you have the word sent in the stack and letter and punctuation in the buffer. Now, is the relation? Yes, there should be a right arc relation. So, right arc means letter will go to the stack. Yes, again there is no relation between letter and dot, the punctuation. What should I take? Is there a relation between any other word in the stack with the buffer? Yes, sent and punctuation are related. So, I will do a reduce here. Now, sent and punctuation are related by right arc, and by right arc I will take the dot to the stack. Okay. And this is my configuration. Now, what do you see? Should I go any further once I have reached this configuration? And you will say no, because what is the condition of my terminal configuration? The condition is that my buffer should be empty. So, at this point my buffer is already empty. So, that means I have arrived at a terminal configuration, and that is where I will stop, and I have obtained all the possible set of arcs for this sentence. So, now this is an example we have seen just to understand how to take all these transitions. But does that help you to solve this problem whenever you are given a new sentence? By a new sentence I mean you do not know dependency graph, or you might also ask, if I already know the dependency parse for a sentence, what is the need for doing all these transitions? And that is where the concept of learning will come into picture. So, we have seen here, if we know the dependency graph, we can choose the configurations. Okay. At runtime, whenever I am given a sentence, my whole task is to find out what are the transitions I should be taking at different configuration, and this I will learn from my already labeled data, and this is what we will discuss in detail in the next lecture. That is, how do I use this concept to define it as a learning problem, and for a new sentence, how do I come up with a dependency graph.